supervisor, Ana Chucarro, as well with my collaborator, Jesus Torrado. This is a project why I decided to start at a PhD, even though I've done some research of gravitational waves and I'm highly involved in the UPIC collaboration. This is like my little baby that came to life today when finally the paper appeared on the archive. So yeah, I'm very, very, very happy to be presenting this work here, guys. Okay, so let's get started. Oh, sorry. Okay, so these are the cosmology seminars. I think that we do not have any kind of doubt that we agree that within the cosmology community, we have a pretty standard cosmological model that we denominate the lambda CDM model. Basically, lambda CDM, what it tells us is that, well, only 5% of our universe content is baryonic matter. Whereas slightly less than 30% of the content is dark matter, and the rest is something that we denominate dark energy, that we believe that it is responsible of the accelerated expansion of our universe, the one that we are suffering in now. Part of that, there is an underlying assumption that this model makes, and is the following. It assumes that the primordial fluctuations of the very early universe were Gaussianly distributed. And this statement is essential because this statement is compatible with saying that the distributions, the distribution of our primordial fluctuations follows an almost a scale invariant primordial power spectrum that we can parameterize in terms of a power law with certain scale and certain tilt. This tilt is constrained to be negative so that this power law is actually blue shifted. And this is important most of the times when we talk about the primordial power spectrum in this parametric form, we assume that the simplest scenario of inflation, the simplest model, and with that I referred by canonical slow roll single field inflation. I will go a little bit more in details later. Predicts this kind of primordial power spectrum, and this is not completely true. What it does, it predicts that the primordial fluctuations are Gaussianly distributed in the very early universe, but by construction, it makes the power law to follow this shape, and as well as it does by construction, it solves different, the main interesting and famous problems that we had with our current, with the first observations of the first measurements of real modern cosmology observables that we had some 20 years ago. I'm talking about the horizon problem, the flatness problem, and the monopole problem. The simplest model of inflation solved them by construction. So slow roll canonical single field inflation. Of course, by inflation, what do we refer by inflation? Of course, inflation is simply a period in the history of our universe in which the universe itself went through an accelerated expansion in a very short period of time. This is what we build by construction so that it solves the different problems that I mentioned before. Of course, this is not enough because apart from having a condition that implies that inflation needs to start happening, this is encoded in the first slow roll parameter. Probably you guys have seen it written in terms of the potential or in terms of a scalar field and call it just simply epsilon. This is the definition in terms of the dynamics of the background. And there is another condition that we need to fulfill because, of course, inflation doesn't only need to start happening, but also need to last time enough so that we solve the problems that I mentioned before. And this is encoded in the second slow roll parameter that probably you guys have seen it written in terms of eta, and again, the scalar field, potential, so on and so forth. The reason why I'm using these two definitions is because are the definitions that we have used in this research that I'm gonna be presenting, and because they encode the dynamics of the background. So finally, single field, as simple as saying that there is just one degree of freedom that it is driving inflation. So it's responsible not only of the background, but what is happening with the perturbations. The dynamics are defined in terms of a potential that depends only on the field. And the background and perturbations, as I said, have the same origin, and the kinetic terms of the field are simply canonical, have the canonical form. This is what we refer by the simplest scenario of inflation. So it's important to highlight because the more I grow up into my PhD experience that we take inflation for granted, but this is not true. Experimentally, we have some kind of certainty of what happened up to Big Bang nucleosynthesis. So meaning 3 minutes after the Big Bang. This is where experimentally we were able to go. However, inflation or whatever happened before that, quoting Daniel Baumann, this is literally speculation. We don't know yet. It hasn't been experimentally tested. A direct experimental detection of inflation will be to detect the primordial gravitational waves that are also predicted by, for instance, the simplest model of inflation or any other extensions. There are other ways of testing what it is happening in these primordial times and studying the primordial physics here in an indirect way. So, for instance, studying or comparing with data coming from the CMB or large-scale structure. And this is what I'm going to be presenting in this research, this kind of indirect study of what happened during these times. So lambda CDM, as I said, compatible with a power law that it is defined in terms of amplitude and a till. As you mentioned before, it is blue shifted. And well, the CMB, the best CMB data that we have at the moment, the one coming from the Planck collaboration in the last release, said very clearly that we are constraining AS and NS very, very well. So most of the models that aim to study in an indirect way what happened during inflation or extensions of this simple paradigm, most of the times rely on, well, they know that these are being compatible with these values is something that they need to agree, but they might be deviation. And this is what we are going to be talking about. So there are many extensions of the simplest inflationary paradigm that predicts that some deviations of the power law in the forms of, they are called features, might take place over the power law. So most of the times we talk of features being oscillating or localized deviation of the power law. They can have several templates. The ones that I'm going to be talking about are going to follow more or less these kind of shapes. So they're going to have an exponential envelope and they're going to be oscillating at certain frequency in a broad range of cases. So I probably spent the first 7 minutes or so talking about how well our standard cosmological model agrees with the data, and it's true. I mean, lambda CDM is very robust from a statistical point of, view, if you compare to the data that we have, so large scale structure of the CMB. However, isn't worth deviating from this simplest lambda CDM model that only contains 6 parameters? The straightforward answer is yes, and the reason is because lambda CDM is not able to explain every single detail that we observed right now. Like, for instance, when we have the problem of this notch, when we are talking about features, we always refer to this lack and excess of temperature in the CMB power spectra. But apart from that, there is a more philosophical point of view when we relate to inflation, and is the fact that the simplest scenario, although, yeah, we are able to constrain an S and AS, but they are not giving us much about what is the physics or what are the physics that took place during those very early times. So recently there has been done a lot of renewed interest in multi-field inflation because of the SWAN plan, alpha attractors that are very elegant. But we can't forget that whatever extension of the simplest inflationary model that we test, it still needs to be liked by the data. So how do we do that? I will argue in the next couple of slides that basically a good way of doing that is relying on an effective field theory. So let me just give you a very, very toy view of single field inflation versus effective field single field. So the action that I showed you before on the canonical is overall single field inflation. You have just one field, they find the potential. You know, if you followed a typical cosmology course, you write this action in terms of the perturbations, you will end up with an action up to second term that looks like this in terms of the co-moving curvature perturbation. Exactly the same thing. You could do it from a multi-field inflation point of view. You will play the same game. You will write in terms of the perturbations, and you will integrate something that we call heavy fields. And you will end up with pretty much the same action. However, there is a difference in here. With this action, what you're basically saying is, look, I'm basically focusing on understanding what it is happening with the perturbations, which is what I can actually relate with data. Whatever is happening with the background is encoded in two primordial functions, so epsilon1 that I defined it before, and this C of S, that is the effective inflaton's speed of sound, that is going to be becoming dependent on time. So in this action here, you don't see it because it's actually equal to 1, equal to the speed of light, and using natural units. This is basically the main difference. So from this single effectively action, we could study what happened, what is the phenomenology regarding the data or the predictions, depending on whether you focus on epsilon1 or in C of S, or hopefully an ultimate if we could put everything into the game, although so far it hasn't been done. If you focus on what it is happening with epsilon1 depending on time, you're talking about features from a variable, the slow row parameters. There has been a lot of work done in this direction, and also some constraints with data from Planck 2015. If I remember, I mean, it's important to say that epsilon1 can be written in terms of the potential and the field in single field inflation. So most of the papers that aim to constrain different inflationary potentials at the end, from an effective field point of view, what they are doing is constraining what it is happening with this epsilon1. On the other hand, if you focus on what it is happening with a variable speed of sound, there has been, again, tons of work done in this direction. You will have features coming from having a variable, the speed of sound, and the physical meaning of this variable, the speed of sound, although it's not 100% sure, I'm going to just give you the analogy on field space in case that you have just two fields and you could write an effective action of just one single field that it is supported by a massive one. You will see that this speed of sound basically implies that the effective inflaton is suffering a turn in field space. Fair enough. So I hope that I convinced you that actually EFT of inflation is very powerful to be testing deviation of lambda CDM regarding inflation with data. When we look to features from this approach, what it is important to remark is that we are actually having a look at the primordial dynamics of what it is happening in there. So we are not simply choosing whatever model of sine, cosine, or your template that you would like to have for your feature. We are actually relating the features of what it is happening in the primordial power spectrum to something that has a physical meaning. So unfortunately, this kind of templates hasn't been tested by Planck, nor in any of their release in 2013, 15, and 14. So this was the main motivation why my supervisor, Anna Zuccarro, focused her attention on reductions of the speed of sound and was developing the theoretical model with her collaborators. There was already a lot of interest in testing against the data. So it was work that Jesus Torrado started, Finju, Vicente, Pablo. And this is basically where I enter into the game. So I joined Anna as a master's student. I also did my master's in Leiden, and she wanted me to start preparing for the last release of Planck 2018 data to see if I could continue testing this kind of templates. Because, well, not essentially motivated because Planck release of data got delayed, because there were already some weaknesses pointed out in the data analysis done previously. We decided that it was worth improving the Bayesian pipeline that we had for testing this kind of features in the primordial power spectrum. So we created a pipeline that it is very modular, that it is going to be easily extendable for missing requirements in case that we want to increase the data sets or the observables and so on. And what I'm going to be presenting now is basically the results of building this pipeline, testing these templates and comparing with Planck 2018 data. So the paper appeared today on the archive, so you will find all the details there. Okay, so let's get it started. So as I said, reductions in the speed of sound. We are interested in studying what is happening with this reduction or with this variable speed of sound of the effective inflaton. So here I just played a trick. I split the action that we had before, the action with epsilon of t and cs of t. And the only thing is that I'm written in terms of 1 minus 1 divided c of s. So if you take the minus, basically you will recover this part of the action with c of s here. The reason why I divided the action is to illustrate what was the next step that Anna and her collaborators took in order to compute what was the change in the primordial power spectrum. And it's the following. Of course, dealing with epsilon and the speed of sound at the same time is complicated because you will have to take into account counter terms and, well, sorry, counter terms, cross terms, and higher order terms in the action. So they remain themselves to the cases where the speed of sound is treated to be small. So we can treat this part of the action as a perturbation. They also assume that the speed of sound needs to be mild. I will explain what mild is in my next slide. And also transient. Transient means that basically the inflaton cannot be, that up to a point it will recover the initial trajectory in field space. If you impose these conditions in the speed of sound, on the profiles of the speed of sound, basically what you have is that the change in the primordial power spectrum, what I've been calling features so far, is the Fourier transform. You can recognize here the imaginary part of a Fourier transform of this term. And this term is what I'm going to be calling the speed of sound's profile. So let me very quickly, because this is something that I'm going to be using in the rest of my presentation, call this function u of time. In this case, as I said, the feature is just the Fourier transform of u in conformal time. The change in conformal time is important because we are coming from an effective field point of view, as well as we are imposing this action to be splitted as the one of single field inflation plus a perturbation, so we can calculate the feature. There are some constraints that need to be fulfilled. The first one, it was straightforward. We required the speed of sound to be small, the change in the speed of sound to be small, so u needs to be small. The second one is more difficult to be understood, but also equally or even more interesting, and it's the condition of being mild. Look, we need to impose this condition, which basically means that the rate of change of the speed of sound needs to be small. If you can see here an adiabatic change in C of S. The reason why is because the action that I have shown you before, I have stopped up to second order. But if we want to use perturbation theory and treat this part as a perturbation, you need higher order terms to be small. The next term that we should be worried about is basically a term that is proportional to this S of t or S of tau. This is the reason why these terms need to be, this is why this function needs to be small, so that we assure that the feature is actually the Fourier transform of u. Otherwise, we will be underestimating a lot the feature, the size of the feature itself. So as a summary, we can basically write down all the constrictions that we have from the theoretical model in the following way. Look, u and s needs to be small, but I'm not going to be looking at each point of the function, how small they are. So in principle, I should look at the minimum of the function and assure that the minimum of the function is at least smaller than 1, because u is always going to be negative. It is better that we talk in terms of the absolute values, so you need to trust me here. But basically, if you do the math, you will see that making this restriction is enough to impose it in the maximum of the absolute value of the functions. Because if you remember, I said that we were not focusing on what was happening with the epsilon of t. We are assuming a slow roll. So basically, slow roll conditions still need to apply. So these values of epsilon 1 and epsilon 2 still needs to be much smaller than 1. Fair enough, we have everything. We have the whole recipe ready to start building our pipeline so that we could start doing some Bayesian statistics to constrain u and s. How do we do that? Well, we develop a complex but very modular Bayesian pipeline. We are in cosmology. Unfortunately, we have very few data sets measuring exactly the same time, so we need to rely on Bayesian statistics. So here is the Bayes theorem, in which the posterior distribution, so the statistical distribution of probability of the parameters of interest, is proportional to the likelihood and the prior. So the first question is, well, I have U of tau, this is what I want to constrain, but I don't know which shape U of tau actually has. Exactly, this is what we aim to do. So what we aim to is we take the data and we are trying to constrain which shape U of tau can actually take based on the restrictions that are imposed by the data. In order to do that, we make a reconstruction using Gaussian processes. I will explain them in a minute. Secondly, once that we have U of tau and S of tau, I said we need to validate that the EFT conditions are fulfilled. If this is the case, we produce a feature as the Fourier transform of the profile of the speed of sound that we have just created using Gaussian processes. You will call your favorite theory code or Boltzmann solver. In this case, we have used CAM that we have modified accordingly in order to take a feature in the primordial power spectrum. And you know how it works. This is a sampling procedure. If we compare with the likelihood, if this is some points or some values that are interesting according to the likelihood, according to the data, they will be safe in a chain, and we repeat that until the sampling method has converged. The sampler that we have used for the whole algorithm is Polycore, which is an nested sampler. The main reason why is very straightforward. The multimodal, the posterior distribution of the parameters of interest are multimodal. This was already something known from previous study. And if you wonder how do we actually deal with this massive pipeline, we use Cobaya. So Cobaya is the new CosmMC that has been written by Jesus Torrado and Anthony Luis. It will end it, I mean, at the end of the days, it should be substituting CosmMC. It's fully written in Python, it's very user-friendly. When I started working in this project with Jesus, Cobaya wasn't even called Cobaya. It was an initial project of Jesus when he was a postdoc in Anthony Luis group. So I've seen Cobaya grow. Actually, Cobaya in Spanish mean Guinea pig. So I was the Guinea pig of the code. Jesus used me as a tester, a beta tester of the code, so that he could improve the user-friendly of the code, the user cases, and, well, all possible bugs that were done during the development, of course. So I really invite you that you have a look at Cobaya. I'm very excited about it. It's very powerful. So if you haven't used it yet and you are currently doing some Bayesian analysis work, go ahead. If you have questions, of course, you can always ask me. Okay, so let's go to the interesting part of how are we reconstructing the reduction of the speed of sound. As I said, we are using Gaussian processes. I don't know if everybody is aware of what Gaussian processes are, but Gaussian processes are basically a way of constructing a collection of random points in which each point with respect to the following one has certain dependency that it is given by a kernel. Historically, the kernel was just a Gaussian distribution in which, well, the standard deviation was denominating correlation length because somehow gives the influence of one point with respect to the other. Right now, this kernel can be many different distributions, not necessarily a Gaussian, but, well, the name remains Gaussian processes. So basically here what I'm plotting is just the mean of all possible random realizations of the Gaussian process given a correlation length. And on top of that, I'm forcing the Gaussian process, so the random walk, to go through some points that I'm gonna be calling from now on training nodes. Please be aware that these training nodes are nothing to do with machine learning. I'm just borrowing the name for convenience, okay? So we have some questions when we were thinking about using Gaussian processes for reconstructing our U of tau. Remember, U of tau is the speed of sound profile. When we were thinking about using Gaussian processes to reconstruct this function, there were some decisions that we needed to make. The first one was, of course, choosing the x-axis. So as I said, the definition tells us that the feature is the Fourier transform of u in conformal time. So we decided that we will still do it in conformal time. Some people have tried it to work in number of epochs. Still, it doesn't really matter. It's just a way of making our lives easier. So, well, we decided to be the conformal time. So conformal time equals 0 means sense of inflation. So conformal time is always negative. As I said, u of tau is always negative by construction. So there was another decision that we needed to make, and it is the following. From a computational point of view, it is annoying to be checking every time that you create a function whether the function has become positive, if you need the function to be always negative. You will need to impose certain conditions on top of that. And this is not convenient. And this is what it happens when you're making a Gaussian process reconstruction in linear scale, both in tau and in phi of tau. So in order to avoid this, for sensible reasons, we decided to use a log-log reconstruction. So we switched to a log tau and the log of the absolute value of u, so that we will assure that always be positive with a minus sign, always negative. So the difference between the two reconstructions is that, of course, with a reconstruction in log-log, the correlation length also behaves in logarithmic scales. So that would allow us for templates that has a broader reduction than the linear ones. Still, both cases are sensible. We actually did the analysis with both, but just for simplicity, I'm going to be showing the results in the log-log parametrization. So as simple as that, we still use a kernel that is log Gaussian. We throw some training nodes, we pick a value of L, and we compute the feature, and we check that the values of U and S that we are interested in, remember that is the maximum, fulfill the conditions of our model. There are some intuition that, of course, we developed during the analysis of all these projects, and it's the following. The larger the profile of U of tau extends in conformal time, more Ks will be affected in the primordial power spectrum. The broader, or well, the bigger the reduction in the speed of sound, the larger the amplitude of the feature. And if the reduction of the speed of sound is smooth and is not very sharp, it will give us not very rapidly oscillating frequency features, whereas if it is close to if it is sharp in the reduction, the oscillation on the frequency of oscillation will increase. Still, this is not that straightforward because, as you might understand, I'm introducing extra number of parameters with respect to lambda CDM. I said lambda CDM is just 6 parameters, and here I'm adding on top of that the correlation length of my Gaussian reconstruction and 2 times the number of training nodes that I have, because remember, it's just the position of conformal time, but also the amplitude. So at the end, what I have is L plus 2 times the number of training nodes, so 1 plus 2. The parameters, well, the ones that I'm sampling over, as I said, is the training nodes, the correlation length, and I'm also letting free the slow row parameters for a reason that I will mention now. I carry as derived parameters the EFT parameters of my theory. Because I'm sampling epsilon1 and epsilon2, I also let free and S and R. A priori, I don't know what is the shape of U of tau, because I'm reconstructively on the fly with Gaussian processes. So these 2 conditions need to be checked numerically. We've done a lot of work verifying that in each step, the conditions of the EFT models are fulfilled. Okay, so I have already reconstruct my function. I have a function U of tau that fulfills the requirements that I need, but I still need to verify for sure that the EFT conditions are fulfilled. So this is what I'm going to be explaining now. And this is, we're going into the world of statistics, but this step is very important and essential, and it makes a difference between having a robust a statistical study or not. This is the following. We know that we need to check this condition, and this condition implies basically that we would like to have points in our chain in the sampling method that has values of U and S that are much smaller than 1, but is still much larger than the values of epsilon 1 and epsilon 2. We would like to have the denser sampling in the middle of the interval, let's say. Therefore, if we were directly sampling U max and S max, we will ideally sample not from a uniform distribution. We won't allow U max and X max to be whatever values. We will ideally, we would like to sample from something like a beta function when you have denser points in an interval of your interest regarding the scale that you give and the layers of the function. Just to be sure that you are fulfilling and you have the maximum number of values within the middle of the interval. However, as we are not sampling directly U max and S max, they are derived parameters, and because we are imposing a prior, I am not throwing the training nodes randomly. Of course, I throw the training nodes in an organized way. I throw one with certain correlation length, and if I want to add a second training point, I organize it in time. Because of this, it is not enough that I multiply the rewrite values by an ideal beta prior function, because I won't obtain that naturally. This is something that it is studying within the maximum entropy principle in statistics and has been demonstrated to work cosmologically in the case of neutrinos, for instance, when you treat it as direct parameters. And what it tells you is the following. If you want to have an actual beta distribution in your derived parameters, the function that you need to impose as a prior is the product of your initial prior, in this case, the uniform distribution and the sorting that we have in the training nodes that we are imposing when we create the Gaussian process reconstruction, times the beta function that you want to obtain, divided by weight. And this weight is a probability, as a density distribution of the sample parameters given that it exists a sorting prior, in this case, an initial prior. Ideally, in the ideal world of mathematics, everything will be perfect if these functions will be, we could treat these functions analytically. Of course, the beta function, we know the shape, but a priori, we don't know how it behaves to have a uniform distribution with a sorting prior. So the way of properly calculating this function, the final prior that we would like to impose in our derived parameters, will need to make us to calculate this distribution by sampling them. So we have done that. So we've done is basically obtaining this denominator by performing a simple analysis by sampling the distribution with polycore, switching off everything else in our pipeline. And what you see is precisely what I was mentioning before. If you wouldn't take into account that this weight exists, you won't be doing a beta function, because you already see that having a prior impose certain denser regions in some parts of U max and X max. So this is important. This is something that we have included in our study and makes our pipeline way more robust than it was before. So, okay, well, I have reconstructed the function. I have verified that my sampling is going to be centered in the area that is more interesting from the effective field point of view. So now, if the reconstruction fulfills what it needs to fulfill, it's time to compute the feature by taking it the Fourier transform, as I said before, feed it to CAM. CAM will give us the theory predictions of the CMB and compare with the data. So it's basically summarized in this slide here. So imagine that I throw two training nodes with a certain value of the correlation length. The Gaussian process will give me the function. I verify S and U. I check that everything is correct. I impose the real prior, the perturbativity prior according to maximum entropy. I compute the feature as taking the Fourier transform. I feed it to CAM, and finally I compare with data. So here what you see is basically the difference in the temperature angular power spectrum of the CMB that this kind of features produced. Okay, we do this with polycore, as already said before in the pipeline, and you basically calculate the posterior distribution of your parameters of interest. So in this case, the training nodes and the correlation length. I'm showing here the case for 2 training nodes. We did the study up to 4 training nodes. I will explain later why. But as it was already expected, it is highly multimodal. This is not the kind of posterior distributions that we are used to seeing when we test the lambda CDM model, or any other kinds of extensions actually have more beautiful distributions of the parameters. The rest of the distributions up to 4 training nodes looks very, very similar. So I'm not showing that just because of illustration purposes. So analyzing these posterior distributions up to 4 training nodes allow us to reconstruct what is the profile that is preferred by the data. What is the profile of the speed of sound reductions preferred by the data? So basically, with the posterior distribution up to 4 training points, I calculated all the possible realization of the Gaussian processes, and I calculated the 68% and 95% contour confident contours. And what you see is like late values of conformal time. Remember, late means closer to the end of inflation. The reduction of the speed of sound can be more or less constrained up to tau equal minus 400. The reason is obvious. The data that we are using, the error bars are smaller when we talk about the first, second, third acoustic peak. Everything at larger scales, basically the error bars are huge, and this is why our constraints of the reduction of the speed of sound at earlier times are very poor. Still, we were able to find, when we analyzed the posterior distribution, several maxima posteriori that are worth pointing out. So you might wonder why, or up to how many training nodes you should be doing your reconstruction. When do you stop throwing training nodes? Because remember, every time that we add a training node, we are adding 2 extra parameters. So the penalization is big. Well, this is done for those who know how to do reconstruction. It will be straightforward to answer. For those who doesn't, you need to rely on statistics. Most of the time, some information criteria are used. In this case, I use the archaic information criterion that basically tell us is an information criterion that give us an indication of where to stop based on the penalization that you have in the improvement of chi-squared based on the number of parameters, extra parameters that your theory has. So in our case, we reach the minimum of this Akai information criterion when we did the reconstruction with 3 training nodes. But still, the maxima posteriori that we found analyzing the posterior distributions, the delta chi-square that they have with respect to the baseline lambda CDM, they are not significant. They are not statistically significant. We knew that. We knew that this wasn't a way of demonstrating that this model is preferred by the data with respect to lambda CDM. What we wanted to demonstrate is that there is another way of actually work with features from a primordial point of view based on the analysis of primordial functions and how they behave. That was the goal of the paper. And the goal was also to provide with a robust pipeline, not coming to basically say, okay, there is a possibility that another extension of inflation works better than lambda CDM. That's not the case. So possible maxima posteriori, we have many. You have it in an appendix in the paper. At the end, I decided to send it to an appendix because there were too many. But we have from single reductions of the speed of sound when you're using just 1 training node to, for instance, 3 single reductions of the speed of sound that are concatenated with each other. It is important to say that, I mean, here in this case, each training node implies that there is 1 single reduction, but this is not the case. You can always recover other profiles with a larger number of training nodes. The training node can be placed in whatever position the data likes so that it reproduces, for instance, just 1 single peak by sending, for instance, this training node to 0 and this training node to 0. So we have found also some interesting profiles that we were not explicitly looking for. In previous studies, Jesus Torrado pointed out that it might be that the data has room to actually show consecutive reductions of the speed of sound. But we end up finding this kind of profiles that are interesting because they show some kind of substructure, but that they fit kind of well the data, surprisingly. So this has been, this has been a point of the research that we were not forecasting at the beginning. So, for instance, this kind of profile with this kind of reductions at very early conformal times tries to fit these typical excess and lack of temperature in the CMB temperature power spectrum. So, as I said, I mean, the statistical significance is not good enough in order to beat lambda CDM. So how do we actually increase the statistical certainty? And this implies to whatever model that you would like to test in Bayesian statistics. Well, you increase your data somehow. And in our case, data might be to study new cosmological observables. So for instance, trying to do the same that we are doing here, but with the CMB biospectrum, if a likelihood were viable, which is not the case. The kind of model that we have predicts that the features in the primordial power spectrum and in the biospectrum will be correlated to each other. So that in principle might increase more the statistical significance. The other is using other observables, like for instance, large scale structure data. And for this option is what we are preparing now, but there is still a lot of work to do in this direction. The first one is essential. I mean, most of the work that has been done in features regarding that has been done in features regarding large scale structure has been done using Fisher analysis. In our case, this is not ideal because of the shape of our posterior distribution. So Fisher analysis is not the best because Fisher relies on the fact that the posterior distribution of the parameter of interest is Gaussian, which is not our case. The second one, because I've mentioned that this kind of model predicts some degree of non-Gaussianities, is to take into account this non-Gaussianity effect on galaxy clustering when we are analyzing galaxy clustering data. Most of these models predict that there will be some contribution to the bias of galaxy clustering in the shape of a scale-dependent bias. This is some work that we are doing currently at the moment with my new master student. We are also working in understanding how to model non-linearities. So as you said, well, as you saw, the posterior distribution, well, we need to focus on studying non-linearities in our case, and we cannot rely on another models of non-linearities that has already been suggested for features because of the shape of our feature templates. They have a natural envelope on top of them that probably, well, they are also damped by, they are also damped when you study in non-linear scales, how this behave. It has another extra damping just coming from that. So we are currently assessing if this will impose a very low limit in which kind of features we can test that actually are going to be visible. And finally, I would like to say that we're going to have some problem with the speed. This kind of a study that I've done with the CMB is slow. It takes a lot of computational resources. It has been optimized as much as we could, but there are some things that you cannot avoid. And it's the fact that when you have a very highly oscillating feature, your integration interval for D of K, in the case of the CLs of the CMB bar spectrum, needs to be very, very small, so that you are sure that you are not missing the feature. And that increase each call to the theory prediction more than 10 seconds. So if on top of that, you add a slow likelihood, taking into account that the likelihoods for large scale structure are slower than the ones that we are used to for the CMB, this might be a bottleneck. So let me just sum up what I've been telling you until now. It is important that when we enter into testing features in the primordial power spectrum, we do it from a physical perspective, a physical meaning. And this is done very easily when you take EFT of inflation to be the model that you're playing with in order to get to test extensions of lambda CDM. In this case, you will have like a direct connection between the templates of your features with primordial functions that have some physical meaning. We have seen that, for instance, combinations of multiple reductions of the effective inflaton can take place. That was some of the things that were left testing. We have seen that there are certain superstructure. These kind of templates have not been yet tested by Planck. It won't be tested by Planck. So it was some work that was left doing just to be sure that this kind of models still were verified according to the data. And when performing all of these, we have created a very efficient and flexible and modular pipeline that it is ready to be used for future analysis, very easily modified, including large-scale structure, the proper model of nonlinearities, changing your Wolfman solver, and so on and so forth. So thank you so much for listening until now. And if there are questions, I'd be happy to answer if I can.
Thank you so much. Lovely talk. I am going to ask everyone to unmute, and if we could all